qubit readout, which we already saw some of them in the first class, right? So this is a superconducting quantum computer, right? At that time, I went through very fast. Now I hope that you will be able to understand most of them. So for example, in this case, there's something called Quantum Machines. It's a company. They sell a controller, which is made of FPGAs and other processing units. So from here, you can go through a Python interface. And if you're going to the Livermore National Lab workshop, if any one of you are going, you will play with that interface. That you might send a pulse. Then you will have a mixer, right? For each student, you know this mixer, what it does is just to bring it to higher frequency so that your pulse kind of encoder, right? And then you will send through this string. So this is the direction refrigerator setup. Your machine is at, this controller is at 300 Kelvin. And first, it will go through attenuation in order to reduce the noise. So you will have a large signal. So because you know that it's going to diminish as you go down, right? But at the same time, the thermal noise at room temperature will keep going down. And then you have a few stages. Go to 700 millikelvin, 10 millikelvin, and eventually reach the, you can call it quantum computer. In this particular case, when you do the readout, right, you have a resonator next to a qubit. The qubit is very small, maybe at this point. Okay? And this is the resonator. You have two ports. Now, for a resonator, what will happen? When you have a microwave goes in, it has a scattering matrix, right? For any resonator, if it is two-port or just any two-port system, right? Maybe just call this port 1, and this is port 2. You have a voltage. You have voltage in because this is a microwave, so it's traveling wave. You have two waves going in and going out, right? Pulse maybe going in, right? So this is V1 going in, like the wave. And then you also have output, right? V2. Right? Or I should call it, let's say V2. Right? And then you have the scattering matrix, right? Because you have something going in, you will also get reflected, right? For example, S11 is referring to the one that comes back. It will be V1 minus divided by V1 plus, right? How much is get reflected. So this is like the reflection. And the most important thing here is the S21 for this circuit. Because in some circuit, they are actually measuring the S11, how much is reflected. This one is measuring how much is transmitted. V2 plus divided by V1 plus. Of course, they are complex number. They are all complex number, right? Now, if your qubit has a different state, 0 or 1, the scattering matrix is going to shift, or the peak frequency is going to shift, the maximum transmission. Okay, just take it for granted for now. We will look into the detail later. So the whole readout scheme is that because your qubit has a different state, then your resonator has a different resonance frequency. So by doing this, I measure what is transmitted here through this quantum amplifier. So this one will add the minimal noise to your signal. For those who studied 226 before, we talked about the noise figure, right? Every amplifier will add extra noise to your signal. So the signal to noise ratio is going to reduce when you go through an amplifier. So, but you want to add a minimal noise. That's why this, what they call traveling wave parametric amplifier. I think I'm correct. Tuba. Here stands for, you don't need to memorize it, but it's good to know that you have this thing. It's called traveling wave parametric amplifier, right? There's no active element. So it adds the minimum noise which to it, right? And then you will further amplify it. Now, so some of you we are not discussing here. Maybe I may discuss a little bit in the future lecture, but we discussed in E226 already. Is that in an amplification train, you want to have the lowest noise figure at the beginning, right? You want to have a small rather to have a small amplification, but add less noise. Because all this noise, if you add less noise, all this noise is going to amplify later. So you want to add it less at the beginning. So usually, like your cell phone receiver, the first stage, the what we call it low noise amplifier, is at very few noise, although it has less gain, but then you have a much larger gain later. So here you see that I have a HEMT, high electron mobility transistor, which is usually made by gallium arsenide and aluminum, gallium arsenide and gallium arsenide hetero interface, which we touch upon this a little bit. Remember when we talk about the quantum dot? This is one of the platforms that you can implement the silicon qubit quantum dot because they form the two-dimensional electron gas. And here the so-called high electron mobility transistor is because you form the two-dimensional electron gas and they don't have any impurity scattering because they are formed by actually having the dopant away from where the electrons are. It's good to maybe talk a little bit about. Remember at that time we talked about this band structure. So this is a narrower band gap, gallium arsenide, right? And this may be a higher band gap, aluminum, gallium arsenide. This is an alloy. Again, smaller atom has a larger band gap. And you have this electron confined in this direction. Going into the screen is the direction of the transport. The source is at you, and then the drain is inside the screen, right? The electron is flowing perpendicularly in this direction. When we talk about the quantum dot, we say that this helps us to confine the electron in one direction, right? If you forgot, this is into the wafer, this direction, right? Into the wafer, right? Or into the chip, right? And then, yeah, you can add other gates to confine another two directions, then you get a quantum dot. Don't know if you can envisage this. I don't have picture here. But anyway, this electron, how are they formed? They actually come from the dopant at the barrier. So this ionized impurity is far away from the electron. So they don't feel the Coulomb scattering, right? This is purely device physics. And so they will have very high mobility, particularly at 4 Kelvin. That's talking about maybe 10,000 or 40,000, 100,000, right? What's the mobility of the silicon at room temperature? Even undoped is only in the order of 1,000. So that is very high mobility transistor, right? So this is high electron mobility. And then you have a regular amplifier again on top. Each of them has its noise figure. Right? So this is the train. I send a pulse. You do the necessary attenuation and the frequency modulation. I try to detect how it look like when it come back. And based on how it look like, I know that whether my qubit is at state 0 or 1. Yeah?
Is the excitation and readout frequency propagated on just a single line? It looks like the way it's drawn here.
Yeah, just single line.
So there are two signals. One is going to drive the qubit, the other one is going to use the
Actually, yeah, one signal is going to drive the qubit, and then another. Actually, this is here is manipulation and reset. Yeah, this is like a splitter here, right? So you can, when you want to read, you just send this signal. When you want to manipulate, which is a single qubit or 2 qubit gates, then you go through here. Yeah, but now I'm only talking about the readout. Now, there are a few things we need to think about when you try to read something. You send a pulse into it. Definitely is related to the width of the pulse, how long you use it. If the pulse is long, then it means I have a very narrow spectrum, right? Think about a sine wave, infinite sine wave. Then it only has a delta frequency at that frequency. But if you are a square pulse, a pulse, but finite dimension, for example, like this, right? If send something like this. This one, if you do a Fourier transformation, it doesn't give you the exact frequency, right? It does have a decay, just because, again, uncertainty principle in frequency domain, right? If I make it very long, then it's very precise. But, so it would be good if I make it long. But the problem is, the readout time is long. And in many quantum algorithms, you need to read it many times. Then it is not good. Particularly, I want to read it many times because maybe before something happened to my qubit, right? So we want it to be short. But when it is short, then it's going to have a very wide spectrum, right? In the frequency domain, this is f, right? This is time, right? If I have a, maybe I should change the color, right? Right. If I have a longer one, let's say this one, right? Then I will have a sharper peak. Okay, in the frequency domain. Yeah. Another thing is the energy. If you have a very large energy, probably it will be good, higher resolution. You are less insensitive, more insensitive to noise. But however, when your energy is too large, you actually can cause some modification to the qubit or the qubit next to it, right? So you also want to have a small energy. Now, for example, here, this example is the readout pulse has negative 47 dBm, right? I mentioned this earlier already. What is dBm? It's just the power divided by 1 millivolt, and then you take the log scale times 10, right? This is dBm. For example, if you are 1 millivolt of power, then you have 0 dBm, right? Negative 47 dBm is talking about more than 100 times less than 1 millivolt, right? And you keep going down, eventually become 123 dBm. It's more than minus than 60 because the cable also has some attenuation. When you reach this attenuator is negative 123 dBm. You look at the power, it corresponds to only about 300 photons. Yeah.
How do you translate the power to number of photons?
So, okay, 1 millivolt is the power, right? So it's energy per second. Now you know your pulse width. And you also know how much energy a photon has, right? H bar omega. Right. Your number of photon times h bar omega divided by your pulse width should be equal to the power, right? Total energy divided by how long it is, that is the power that you have. Yeah?
That's log 10, right?
Log 10, no, I mean just the power, and then you do this divided by 1 milliwatt log 10, then it becomes dBm.
Yeah, sorry, I just want to make sure that the log isn't like...
Okay, I see what you mean. Yeah, this is log 10, correct.
Okay.
Yeah. Okay. Okay, so this is and then what else? The quality factor of your resonator is also important, right? Because it's going to affect, because you're not measuring your pulse, you actually measure your pulse after this resonator, which is equal to the S21 times this spectrum. Okay? So any question about how you read a qubit in superconductor qubit? Yeah.
Good.
I'm still a little confused as to, like, so when you read a qubit, it's going to collapse into, it's in a superposition in a 0 or 1 state. But like, how does, if reading out is just sending in a pulse and manipulation is just sending in a pulse, how does one collapse the wave function but the other doesn't? Two different frequencies.
Yeah, of course, they're different frequency. So this, I really don't know how to say this, right? It's related to, You're sending a pulse to it, then you make the Hamiltonian, you create a Hamiltonian, then evolve, right? So here what it really do is this is pretty philosophical, but there is a more deeper framework, probably I don't know. But
this is a non-destructive readout, correct?
No, this is going to be we need it to collapse. I'm talking about it just collapse. So this will just like the spin, right? How do you read it? You read it because you measure it, then you get the energy of the photon, for example, right? If I'm spin up, then you measure the energy difference. Once you do this, then you get the information, it has to collapse. But I do not see that, I don't think there's or maybe I'm wrong, right? There's not a simple theory telling that how you go from a state to collapse.
Right. So this is just like a whether you actually look at your measurement or not type of situation. Or not in practical sense, like, but yeah.
I would say that this is just like you send a pulse. If I don't look at it, then it is not collapse. What I'm thinking is if you send a pulse to the qubit, reading pulse, but you don't read it, then it won't collapse.
Right.
That's what I understand. I only understand to this level. But you look at the output pulse, then you collapse. You agree what I'm saying, right?
Yeah,
Except
I
that.
understand what you're saying.
Uh-huh.
I just like, I'm not
Not really human element. Is that whether we measurement is like entanglement. Whether we make this result and entangle it to the larger environment. Yeah. Okay. Anyway, so yeah. So that's a good question. But what I want to say is that your question is really asking about what constitutes a collapse and what does not, right? So which is a broader question that I don't know how to answer.
My understanding is this is a non-demolition, because, well, let's say if you're talking about, let's say we discuss spin qubits, right? Which deal with electrons. Usually when you're doing polyspin blockade experiments, it involves tunneling electron from one place to another, usually a reservoir, so that electron is lost. So as a result of the readout, right, you can still do the measure, but now that electron is lost, so that's called a demolition kind of a readout method. Whereas I think usually reflectometry does not involve that kind of operation. You have a qubit in a certain state, you apply a pulse, you read its state, and that state of that qubit is still retained.
You cannot. If you get 100% certainty of the state, then it is collapse. Okay, it's impossible. You cannot like read a qubit. There's some like quantum like tomography or something more fancy, but they need to give up some information. If I really know that is one, then it has to collapse to one. That's just quantum mechanics. Yeah, they have some trade-off. Like, okay, I not 100% collapsing it. Actually, his advisor was working on this, right? She was like working on this, not, how to say, I forgot what she's doing, but weak measurement, right?
I have Dr.
Yeah. Yeah, I saw her presentation, like weak measurement. So that, yeah, so I also don't understand completely or mostly. Yeah, but if you just think that I 100% read it, I know it is one, then you need to collapse to one. You cannot say that I still have a chance in a superposition.
Why did that term?
There's another thing I don't know well, but for sure, but that is like whether you can still keep something. Yeah, I don't know that well. I cannot answer you. Okay, but do not mess up this with this. Yeah, I think they're different. Okay, yeah, thank you. Have a question?
Professor, I didn't understand.
Say again, or this one? So you can have these are two ports from this machine. It can send out two different signals. They are at different frequency. So here it's just that if I want to read out, I will go through this path. This is a combiner or a splitter night structure. So it will go through here. You just to save the cable, I only have one port going into here. So you can either choose when you want to do reset of the qubit, then you send out the pulse from here. You disable this part. Yeah. Okay. Yeah.
So, yes, based on what we just talked about the readout pulse, if you have a certain SNR that dictate how much integration time you need, that would dictate how much your readout pulse with,
Yeah.
in order to detect. Right? Now, if you do more than that pulse, okay, that just gives you more signal. And when you're doing averaging, you can get a much more better fidelity of the measurement. But I guess you don't, there are two things happening here. One is the spectrum and how it interferes with other hardware on that, and how much readout fidelity you want out of the system. Are those two things tied together, determining how much exactly this pulse width for the readout?
Oh yeah, because if you have a lousy S21 very broadband, then you cannot distinguish the shift, right? So I just told you that the qubit is going to change the resonator frequency. If yours is very broadband and you shift a little bit, you cannot distinguish these two shifts. Okay, I will go to detail later, right? But what you are reading is not the pulse, it's the pulse times this times the S21. So both of them has an effect to help you to distinguish whether it is 0 or 1.
But
Yeah.
the superconducting resonators are very high.
High Q cannot be infinity. We are talking about some very small number here, right? Look at the photon. There's always a limit, right? Yeah, you say it's high Q, then you cannot just say that I don't care about the Q. You need to, because it's not infinity.
Okay, and how much frequency shift are we talking about?
So let's take a look later, okay? Okay, so now let's just go to some basic, more hand-waving thing. So again, this idea of readout is like what people do in the atomic physics, optics, right? So you have atoms that you have two levels, 0 and 1, or ground state and exciter. Then you have a cavity, an optical cavity, and then you can have a photon here. And you know very well a photon can be absorbed by this atom, and then atom will go to a higher energy level. The atom can also go to lower energy level and then emits a photon, right? If the condition is right. Now we have learned about Hamiltonian. Now looking at this equation, I hope that you won't be so scared and you start making sense out of it, right? We are not going to derive this equation, but look at this. What is A dagger A? Yeah, it's annihilation creation operator, annihilation operator, but what's A dagger times A? N. It's the number operator, right? So basically here is talking about how many photon inside this cavity, right? Because this Hamiltonian is h bar omega n plus 1 over 2. So you naturally feel that it makes sense, right? We did not derive it, but this one makes sense, right? And then how about this one? H bar capital omega divided by 2 sigma z. This one looks like what? What Hamiltonian is that? Yeah, looks like the spin qubit, right? This looks like the omega looks like the Lamarck precession frequency, right? Yeah. So this one again, it makes sense. Just talking about the state of the two-state system. Definitely, last time I showed you that the superconductor qubit can be mapped to a broad sphere to map to a spin state, right? So I would expect this type of Hamiltonian, right? Here is telling me whether this guy is at excited state or ground state. Make a lot of sense, right? Now, these two terms you can ignore it. It's talking about the leakage. For example, your photon can leak out of this cavity because your mirror are not perfect. Your atoms also can lose energy without generating the photon for some non-radiative decay or other two-level system. That is also understandable. I lose energy through other way, right? So this is just how it loses. We can ignore this. Look at this. I don't know if you can make sense out of this. A dagger sigma minus. What will you say? Now you have learned second quantization, at least hand-wavingly. What is the meaning of this term? If you apply to the basis states of this number operator and also this spin or this 0-1 state, right? When you apply sigma minus, maybe you kind of forgot. Let's start with A plus, A dagger. What does it do again? Yeah, no, A dagger is, raise the energy. It means increase one photon, right? Sigma minus, you probably forgot, we kind of did that when we are doing the spin qubits with the rotating magnetic field. At that time, we introduced sigma minus equals to, I also forgot the exact form. Sigma x plus I sigma y. No, minus I sigma y, it should be minus, right? We might want to divide it by 2, but let's take a look again what it is. What is sigma x? 0, 1, 1, 0. What is sigma y? It's negative 1 on top, negative I on top, I at bottom, right? So this is negative I times negative I, then what do I get? I get negative I times negative I. Negative 1. Negative I times negative y, I, right? I'm talking about this. 0, negative I. I times I equal to negative 1, right? And this becomes, what is at the bottom? Negative I times I. And what do we get? 0, 0, 2, 0. This one is what? This is a lowering operator, right? I did not multiply it by 2, but it all depends on the context. But this is just normalization. I can make it just divide it by 2. Let's apply this to the higher state, 0, 1. What is this? 0, 0? No, I do it wrong. 1, 0. It gets 0, 0 and 0, 1, right? It just flipped the state from higher state to lower state. Of course, we need to define now this is the higher state, this is the lower state, right? Make sense? This is 1, this 0. So this is a lowering operator, right? Isn't that this is kind of saying if apply this to the bracket of this combined system, it kind of saying that I move the energy from the high level to the low level, and then I increase one photon by A dagger. This term is saying that I reduce the photon, remove one photon, but I excite the atom by sigma dagger. Sigma dagger is the raising operator, bringing me from the ground state to excited state, right? Do you get what I mean?
So A is the
creation operator.
So you add 1, so it's going to get excited.
No, you add one photon, but where does the energy come from? By reducing the atom from upper state to lower state. So it's just talking about the creation of the photon because emitted by the atom. Here is basically saying the destroy of a photon and excite the atom.
Isn't it the other way when it goes to excite?
Yeah, it absorbs the photon, right? A is absorb photon, right? Lowering operator. Lower the quantum number of photon. A is for photon. Sigma is for the atom state. Okay? So we have this G parameter, which is the coupling strength, right? If it is 0, then you don't have this term. These two systems are completely isolated, and it makes sense. You have your own spin system, and then I have my own cavity, right? They never talk to each other. And then if I have some coupling, then they start talking to each other, right? So this one take a long time to derive. Of course, you can read this paper, take your time if you enjoy, right? Otherwise, it now looks very familiar and comfortable to us. I hope that you feel so, right? So what happened to this one? It is like that. we have if you look at the left, before they are coupled, I have the up states of the atom and down states of the atom. And then for each, for the cavity, I can have 0 photon, 1 photon. Right here is talking about the number of photon. Number of photon. 0, 1, 2, 3. Right? I add more photon, of course my energy will go up, but my atom is still spin up. Another thing is that I might have spin down. So in this system, the spin up, spin down has a higher energy. So just take it for granted. So when I have 0 photon, then I have, of course, a higher energy, right? And you see the difference is the same because in this case, omega r equals to capital omega. This omega r equals to capital omega, right? So the level difference on the atom is the same as the level difference in the cavity, right? When they are uncoupled, when they don't talk to each other, when G equal to 0, this is G equal to 0, G equal to 0. They are unrelated to each other. But if you solve the Hamiltonian, right, you actually will find that it got split, right? Because when you have coupling, we don't talk about this here, but just from quantum physics, you have 2 levels, you're going to split because of degeneracy, that they will push against each other. Just like your atomic orbital. When you put 2 atoms together, the 1s orbital will start splitting against each other. Put 3 atoms, then you have 3 different levels. And that's why you put many atoms, you become a band, a conduction band of the energy level, right? So then they will split. Now, in this sense, nothing is interesting. Why? Because when I am upper states, right, the atom is spin up. Now, if I try to shoot a photon across this cavity, it might excite it from 0 to 1 because now I have 1 extra photon. This energy is the same as when it is ground state, right? I shoot another photon to it, and then it might excite to another level. They are the same. They have the same energy. So I cannot measure whether the atom is spin up or spin down. Okay? But if we do something called detuning, which means the cavity resonance frequency of cavity and atomic transition frequency are different, then you see that there will be a splitting. Look at here. There will be a split. It becomes the dashed line. When it is pointing up, when it is up state, which is actually the ground state in this case, the energy it needs to add a photon into this cavity is omega r minus g squared divided by delta, instead of just omega r, right? Originally, you think that if I want to add a photon to the cavity, I need to add 1 omega r, right? H bar omega r. Make sense? Just the Hamiltonian. But now, because of the atom, the state of the atom, it is smaller. It becomes omega r minus g squared divided by delta. And it makes sense because this G is how strong they couple to each other. If they don't couple to each other, then I don't shift anything. It also depends on the amount of detuning, right? On the other hand, if your atom is pointing down, then you will take omega r plus g squared by delta, right? So now you see that if they are coupled, the amount of energy I need to add 1 photon to the cavity is different depending on the state of the atom, whether it is ground state or excited state. Yeah.
Excuse me, what is coupled to what here?
The atom is coupled to the cavity. The cavity has photon. This is just 2 mirrors. So the photon just bounce back and forth, right? It's a standing wave. 1 photon, 2 photon, 3 photon. The energy is h bar omega r. Inside this cavity, we have an atom. And the atom has nothing to do with the photon outside. You just have the electron going up, down in its state. But when they talk to each other, then you have some coupling. Because the electron can absorb the photon or can release the photon, right? And then you have some coupling strength C. So in this case, you change the cavity's property, overall property. It's no longer that adding one photon need h bar omega r is depending on the atom energy level. One is omega r minus g squared divided by delta. Another is omega r plus g squared divided by delta. In simple word, it's just that the existence of the atom changed the resonance frequency of the cavity. Okay, I actually don't expect you to know this math in this class. But I try to explain to you, and then I only want you to take one word home. It is the existence of the atom changed the cavity's resonance frequency. And it changed it in different ways, whether it is at ground state or at excited state, which is understandable. I think so, right? Just my car, if you add one more person, whether you add an adult or a kid, it's going to change the resonance frequency of my car, right? Okay? So that's why you have this detuning. It changed the energy between when you go from spin up 0 to spin up 1, means you add one photon, or spin down 0 to spin down 1. They are different. So what? Yeah.
This word detuning also comes in the context of silicon qubits. Is there some parallel between?
No.
Completely different.
Not in that case. In that case, detuning, we were trying to look at the frame. We are not talking about this cavity. Yeah, but yeah. So then what else? Then what's so important? I mean, explaining this because I want to link you, because that's how people develop the framework. They have this circuit QED, circuit quantum electrodynamics, which you learned already, right? We already learned how to quantize a LC tank, how to learn quantize a transmon circuit, right? What they do is the same idea. Here is a cavity. Okay, so this is a transmission line. This is an IC chip layout on a plane. You have this ground plane here, and then you have the signal going this transmission line, and then make an opening here. And then you only have a standing wave that is possible to reside here classically. And because this is open, to satisfy the boundary condition, you see that this has the maximum amplitude at the end. So you can have different mode, right? You can have this L. For example, you can have the lowest mode is L equals to lambda divided by 2, right? Because this is your L, this is your cavity L, and then the wave can go from maximum to negative maximum. So I'm wrong, equal to, am I right? Yeah, this is lambda divided by 2, right? Yeah, this is lambda divided by 2, right? This is a half wavelength, right? Yeah? So this is, the maximum is lambda divided by 2. What we are showing is, here is another mode, 2, lambda, right? Equal to 1 wavelength. But doesn't matter. The point is, you have a question? Yeah.
So the wavelength is fixed?
Say again?
The wavelength is fixed?
Wavelength is not fixed. You can, depends on what microwave you shoot in, but only for the wavelength that match lambda divided by 2, lambda, 3 lambda divided by 2 can form a standing wave here. And only those that can transmit through. Yeah. Otherwise, they cannot. Yeah. So this is the cavity. And then here we have a transmon qubit. Okay, it actually has 2 Josephson junctions, but I don't want to go to detail. But the point is that it acts as an artificial atom, Cooper pair blocks. Why? Because it has 2 states, n equal to 0 or n equal to 1. 0 extra Cooper pair versus 1 extra Cooper pair. And they are coupled to the transmission line through a capacitor, right? You don't see it, it means it's a capacitor because the rest are just insulator, right? These are all niobium or aluminum superconducting. This is the schematic of this circuit. You have transmission line, and then this is the CG. Remember the CG we had when we do the qubit manipulation, right? And this is the 2 Josephson junction, 1 qubit. The reason of doing this is to have a so-called flux tunable qubit. which we did not study. Like if you put two Josephson junction in a loop, you pass through the flux, you will be able to tune its Josephson junction energy. Okay, and but remember, Josephson junction energy is going to determine the inductance and thus all the resonant frequency or whatever, right? But that's all I want to say. You get the same thing. Your Cooper pair may be 0 and 1 extra Cooper pairs. Then you can have one photon. Again, this is photon. This is EM wave. Electromagnetic wave. They are all photon, but just a photon with a very long wavelength that we cannot see. Even longer than infrared, right? Microwave. So you can have one photon, two photon, three photon, and they follow the same energy landscape. Okay? And again, because of the pooling, they follow the same equation, the same Hamiltonian. And so you have the same thing. When I have 0 photon and 0 extra charge, I can go to 1 photon and 0 extra charge if I absorb a microwave photon with this energy, omega r minus g squared divided by delta. But when I have 0 photon but 1 extra Cooper pair, this is Cooper pair, it's just like the excited state, I will absorb 1 photon to this resonator if the frequency is omega r plus g squared divided by delta. Is this okay? Just parallel to what we discussed before. Again, it's saying that the presence of this artificial atom will change the resonant frequency of this resonator, which is possible, right? It's nothing strange, correct? I have a resonator. It has a peak transmission frequency. I add something into it. Definitely it's going to change the resonance frequency, isn't it? But it just turned out that the spin up and spin down has a big change already. And that's how we know. I'm not spin up, spin down, the 0 and 1 state. And that's how it changed. Okay?
So, sorry, just to capture the summary here. So the photons are captured by the transmon, and in that...
It doesn't capture by transmon. The photon is in the resonator.
Yeah.
The transmon does not capture the photon.
How do you lose a photon? What happened? You have a change in frequency, right? That's because of...
Change of the resonant frequency. I'm not trying to change any photon.
Okay.
Yeah.
Change in resonant frequency. That happened
Because of the system, the coupling. Because now the system not purely these two terms. The resonance frequency of this resonator without the transmon is, let's say, 5 gigahertz. Now I put a transmon there. In principle, you should expect that the whole system resonant frequency will change.
Okay, now when you keep adding
And now, if I don't have extra Cooper pair, it will change by certain amount. And if I have 1 extra Cooper pair, it changes by another amount. And because they change differently, then I will know that whether it has 0 or 1 extra Cooper pair by looking at its resonance frequency. Make sense? Yeah. So this change, right, this g squared divided by delta is called the cross cut. This is something you need to do in your project, okay? Your goal is to maximize the cross cut, but it can have other problem. But naturally, you will see that the cross cut larger is better, right? Because I can distinguish them. If this cross cut is 0, it means whether you are 0 or 1 state, you have the same resonant frequency. Then how do I know whether you are 0 or 1, right? But just so that what people will say that how much the cavity resonance frequency is pulled by the artificial atom. But this is only valid when the capacitive energy is much larger than delta. Okay? A more accurate equation is this, right? No need to memorize, no need to put in your cheat sheet. Just need to know that when you, in the future, you need to do calculation, refer to this paper. Okay?
And G is just the coupling strength?
Yeah. just the coupling strength.
Can you explain this cross? What is the cross current?
Again, what is g squared divided by delta? It goes into these two equations, right? It's going to see that how much energy I need in order to inject one more photon when the state is 0 in the transmon. And it is by omega r, the original resonant frequency, minus g squared divided by delta. And here is saying that when the state was 1, how much more energy I need to, or what type of photon frequency is needed so that it can go to another state. Now it's plus g squared divided by 2, right? So this is how much the transmon change the resonance frequency of the resonator. And that's called cross curve. Yeah.
So the higher.
If it is high, yeah, because they are distinguishable, right? And that is here just to recap what happened, right? So that is from quantum mechanical point of view, hand wave thing, we say it absorbs one photon and take one photon. And then from macroscopic of view, it's just saying that the transmission S21, when I have this voltage goes in, and then I go out, then I will have a transmission spectrum like this. When it is 0, it's peak at omega r minus g squared divided by 2. When it is 1, it's peak at omega r plus g squared divided by 2. Then you think of a way to measure it so that you know that whether it is on the left or on the right. We will talk about that later. Okay, so that's it. So I think I say something wrong. By definition, it should be V2 because going out is minus, right? So maybe let me correct now so that you won't get, all right, the one going out should be minus. Okay, so this one should be V2 minus into V2 plus, just convention, okay? For those who know microwave, you should know that. Yeah.
So in this graph, is it like we measure?
This graph? No, this is not measurement. This is the S21. So it's the property of the resonator, right? It is saying that if I have this frequency, then you will get this output. Have this frequency, you get this output. You input this frequency, you get this output. So this is just the property of the resonator, S21. Let's take a deeper look, right? So this one is a simulation I done before. It's a 3D cavity. This is a pot, right? You go in and then go out. This long one is a sapphire substrate. So insulator, aluminum oxide. And then this is the resonator, just a strip of the superconducting wire. Okay? And then you will put a qubit next to it. But basically here I simulated the real part and also the imaginary part of the, I plot the real part and imaginary part of S21. So look at the real part, which is the blue. It starts from 0 and then we'll pick up like this. And then the imaginary part is like this, right? While earlier, what I show you is the magnitude in the other figure. The magnitude will be something like this, right? So if you really plot them together, for example, you will see something like this. This is the resonance frequency, right? This is magnitude of S21. Is this okay? Yeah? Now, if I have cross curve, what happened? The spin up may be 0 may be here, and 1 may be here. Because they got shifted by 2 g squared divided by delta. Yeah.
You said spin up. I'm confused now.
Not spin up, 0. Just 0 state and 1 state. Okay. So now, how are you going to measure it so you know that whether it's 0 or 1, right? So usually what we do is to measure at this point, at the middle. We are going to send this frequency. Now, when you are 0, it's a little bit difficult. When you're 0, you have this blue, this negative blue, right? But the real part, let's say it is 0. But if you have 1, your real part, so I say it wrong, should be the real part is blue, right? So when the state is 0, your real part is negative. But when your state is 1, your real part is positive. So I just measure that frequency. If I get negative, I know, oh, this is 0 state. If I get positive, I know, okay, this is the 1 state. Right? And that is exactly what we would do. And here again, show the real and imaginary part in log scale, in power, forget about it. But the point is that you have noise. These noise are going to mess up. Think that if your core square is not large enough, and then you have a lot of noise here, let's say the noise is that large. Then for negative, sometimes you get positive. For positive, sometimes you get negative. Then you don't have fidelity. So for example, in this case, we have the enough separation, enough power. Then you see that after measuring 2,000 points, 1,000 for each of these, sometimes this simulation looks good, but in measurement, sometimes you have some green point which is supposed to be 1. It gives me negative, for example, right? And sometimes it's supposed to be 0, which is the blue here. It gives me positive. And these are the fidelity problem. This is the error, right? So I have finished discussing how to do measurement, readout. Any questions?
What did you choose a superconducting cavity instead of just a superconducting qubit?
No, then you have high Q, right? You cool down everything to 10 millikelvin. Of course, you want to use superconducting cavity. If you are using metal, cavity is a metal, right? Usually, resonator. You use resonator to make a cavity.
You can build a resonator with a cavity, or you can actually build a
Oh yeah, because 3D, you are talking about why we do 3D, right? This is not my idea. It's from Livermore National Lab, and this has very high Q. The Q can go to million.
correct. So, okay, yeah, this will be a better technology.
Yeah,
Very speed, no?
yeah, yeah. But they need a high Q to explore all those things. So yeah.
Or like,
Like high Q, you can reduce or reduce the leak out of the photon. There are many things that you want to have a high Q cavity.
okay,
Yeah.
but like in terms of technology roadmap, do you think this is a viable platform for if you're trying to do a lot of qubits?
I cannot comment.
Because I mean, it seems like, I mean, it's